Hello again. We're now going to talk about one of our supplemental sections, which is on rational equations. We have already dealt with this before. We've talked about rational functions. Now we're talking about solving rational equations. We've actually practiced this on a few problems in previous sections, so it won't be completely new. What will be new is when we have a rational equation with a variable in the denominator, we have to watch out for false solutions called extraneous solutions. Let me share my screen and we'll get started. Let's take a look now at problem number 1. In problem number 1, we are asked to solve the following rational equation. If there's more than one correct answer, we'll enter it separated by commas. If there's no answer, we'll put in none. Our equation for number 1 is 1 over a plus 2 over 9 equals 1 over 2. This is a rational equation because we have the ratio of two things represented inside of an equation. We have an equals and something on both sides, and we've got fractions. That's what a rational equation is. Notice that we also have the variable in the denominator. By looking at these originally, I know that a cannot be 0. If a is equal to 0, I violated one of the primary rules in mathematics. Thou shalt not divide by 0. So a cannot be 0. 9, however, doesn't cause a problem in the denominator, and neither does 2. We could keep the fractions and get common denominators and combine them that way, but that's a lot of work. It'd be better to get rid of the fractions and then solve for a. To get rid of the fractions, we look for the lowest common denominator. We have 3 small denominators, a by itself, 9 by itself, and 2 by itself. Over here, we're going to make a list of the common denominators in order to build the lowest common denominator. A by itself, 9 by itself, and 2 by itself. 2, of course, is equal to 2 times 1, and 9 is equal to 3 times 3, which I've moved out to the side of the 2. A, of course, is different from both of those, so I push it even further to the side. My lowest common denominator needs 1, 2, 1, 3. Oh, no, it needs 2 3s because it needs that 9. And it needs 1a. Now multiply the 3 or 4 factors together. 3 times 3 is 9, times 2 is 18, so we get 18a. You don't have to do it this way, but this is a good technique on finding it, where you break it down into its prime factors. Since the lowest common denominator is 18a, I want to multiply everything on both sides of the equation by 18a. There are 2 ways of writing it. You could put the entire equation in parentheses with 18a on the outside and then distribute. Or, and what I prefer to do, is to write it on each individual term. Remember, terms are separated by plus signs, minus signs, or equal signs, where the plus and minus are not inside parentheses, not inside fractions, and not under radicals. They also can't be in absolute values. That would give me 1 over a times 18a over 1 plus 2 over 9 times 18a over 1. Oops, that's a 1, equal 1 over 2 times 18a over 1. Now let's go ahead and simplify before we multiply. I have an a factor in the denominator and an a in the numerator. When you found the lowest common denominator correctly, the denominators will always cancel. This leaves 18 for the first term. And the second term, 9 does divide 18. 9 divided by 9 gives me a 1. 18 divided by 9 gives me a 2. That gives me a 2 in the numerator multiplied by the other 2, which gives me a 4. The a tags along to give me 4a. Then I have a 1 over 2 times 18a over 1. 18 is divisible by 2, and that will leave behind the 9a. The next thing I want to do, of course, is combine my like terms and get all my a's together. So I need to isolate my a terms. Again, I'm trying to find what a is that makes that rational equation true. So I want to isolate the a terms. Since I don't like negatives, I look at the two terms and I say, well, 4a is smaller than 9a, so I'm going to move the 4a. It has the added advantage that the 18 is already on the left and I don't have to move it. Then I get 18 equals 5a after I subtract 4a from 9a. Then I'm going to divide both sides by 5 so I can isolate a. A turns out to be 18/5. Now I have to do something that I've not had to do in the past in the examples we did previously, because in the examples we did previously, we didn't have a variable in the denominator. Now I'm going to, after isolating a, check for false solutions. These are called extraneous solutions. Extraneous solutions are solutions that don't actually work. Where do they come from? They come from the original problem's denominators. Whatever was in the original denominators, it can't be 0. So a cannot equal 0. But I didn't get a equals 0, I got 18/5. So the answer is 18/5. Let's look at problem number 2. Problem 2 is very similar to problem number 1. Again, we see that we have v in the denominator, so v cannot equal 0. I will let you solve this one on your own since it's so similar to the one we did previously, and we'll move on to the next problem. This one is a little bit different because it has a p squared and a p in the denominators. It also has a term that's not already a fraction. Let's take a look at this one. Now we have the equation 1 plus 9 divided by p equals -18 divided by p squared. Again, we know this is a rational equation because we have an equals and something on both sides, and we have fractions with the variable in it. This means it's a rational equation. What are the values that p cannot be because of the original denominators? Well, definitely p cannot equal 0. In fact, p squared also gives the same solution that p cannot be 0. Make sure you put the slash through it to indicate not equal to 0. Now we build the lowest common denominator. My little denominator of the 1 isn't written, but it could be. I could rewrite the 1 as 1 over 1. Remember that any term that does not have a denominator can be made into a fraction by dividing it by 1. 1 is one of my denominators, but 1 doesn't generally affect the lowest common denominator unless it's the only thing there, in which case, why are you looking for the lowest common denominator? Then we have p, which of course needs 1p by itself, and we have p squared, which needs 2 p's. I line the first p up and underneath the first one, and then the second one goes out by the side. I need p times p, which equals p squared. That's my lowest common denominator. Now I'm going to multiply every term by p squared, whether it was originally a fraction or not. If I don't multiply every term by it, I've unbalanced the equation, which we know makes the solutions not work. Now we take the 1 over 1 and we multiply by p squared over 1 plus 9 divided by p times p squared over 1 equals negative 18 divided by p squared times p squared divided by 1. Now we can simplify. 1 times p squared is p squared, and when it's divided by 1, I might as well just write p squared. In the second, I have a p in the denominator and 2 in the numerator. The 1 in the denominator cancels one of the 2 and leaves me with 9p for the second term. In the third term, on the right side of the equation, I have p squared in the denominator and a p squared in the numerator. They cancel completely and leave me with the constant negative 18. Now I need to look at this equation, decide what kind of equation it is, and figure out how to solve it. It's got a p squared and a p term and a constant term, which tells me it's quadratic. I can solve it by the square root property. I can solve by factoring. I can complete the square and then use the square root property, or I can use the quadratic formula. I'm going to try factoring since that's usually the first thing I try. It's the fastest if it works. The two methods that always work are completing the square and using the square root property with it, and the quadratic formula. In order to do any of these methods, I need to put the negative 18 on the left with the rest of the equation and get 0 on the right. We call this standard form. That gives me p squared plus 9p plus 18 equals 0 after I add the 18 to both sides of the equation. Now I want to try to solve it by factoring. When I split up the p squared, the middle term tells me it splits as p and p. The last sign before the constant is a positive, which tells me they're the same. This then tells me they're both positive. I need two numbers that multiply to give me 18, but add to give me 9. 1 and 18, nope, that's 19. 2 and 9, no, that's 11. 3 and 6, yes, that's 9. Now I want to solve using the zero product property. That says when two things are multiplied together and you get 0, one or the other or both are 0. That means that I can solve each equation individually and I get two possible solutions. I get -6 and I get -3. The last step in a rational equation solving problem is to check for false solutions. Check for those extraneous solutions. Go back up to the top where you started and wrote down what the original denominators cannot be to find out what is eliminated from your possible solutions. Only p equal to 0 is not possible. Since I didn't get p equal to 0, then I circle both of these as my solutions. I'll put them in a comma separated list. -3, -6. Oops, that's a 5. There's the 6. Let's take a look at this next problem, which is a lot more complicated. Looking at number 4, we have the fraction 7 divided by z minus 7 minus 2 divided by z plus 7 equal 5 divided by z squared minus 49. Now, when we're looking at these equations, the first thing we need to do is make sure that the denominators are fully factored. We haven't had to do this before because they've been single terms. Now we have multiple terms in the denominator, so we want to make sure the denominators are factored. If you've left space, you can factor directly below. Z minus 7 doesn't factor anymore, So we're going to put it in parentheses because it'll be a factoring group when we look for the lowest common denominator. Z plus 7 also doesn't factor anymore, so we put it in parentheses to be a group when we look for the lowest common denominator. In fact, we can go ahead and start building it over here to the side. We're going to need a Z plus 7 group and a Z minus 7 group. They're not the same group, so don't line them up one above the other. Now, what does this last denominator need? It's Z squared minus 49, which factors, not surprisingly, as Z plus 7 times Z minus 7. It needs one Z plus 7 group, which will line up under the other Z plus 7 group. And it also needs the Z minus 7 group. I need one for each column. I need one Z minus 7, and I need one Z plus 7. This is the lowest common denominator that you can use that will evenly divide out all the denominators present in the original problem. This means that I want to multiply all three of the original fraction in their factored form by the lowest common denominator. But wait, before we go any further, let's figure out what x cannot be. When I'm looking at this denominator, z minus 7, I note that z cannot equal 7. When I'm looking at the second denominator, I note that z cannot be negative 7. Because the factors here are identical to these two, it doesn't add any new information. These are the restrictions on my original domains. Z is not 7 and it's not negative 7. That causes division by 0, which is not allowed. Now let's rewrite the problem in factored form and multiply each term individually by the lowest common denominator. Remember that the terms are separated by pluses and minuses that are not in fractions and not in parentheses. That means this minus does not separate terms, but this one does. Then we want to multiply by the lowest common denominator. Let me create a little more space here. Then I have 2 divided by z plus 7. Again, that's a factoring group. That does not count to separate terms, but the minus does. Then we have an equals, and then we have 5 divided by the factored denominator, z plus 7, z minus 7. Now we're going to multiply by the lowest common denominator on each individual term, separated by the minus sign in the open and the equal sign. That gives me z minus 7 and z plus 7 on the first fraction, z minus 7 and z plus 7 on the second fraction, and z minus 7, z plus 7 on the third fraction. Now, when I look at the first fraction, the 2 minus 7s will cancel, and that will leave me with a 7 and the z plus 7. On the second term, the z plus 7s will cancel, and that will leave me with the negative 2 and the z minus 7 group factor. On the third fraction, the z plus 7 and z minus 7 cancel both of them in the denominator, and I'm left with just 5. The next thing I want to do is multiply everything out so that I can solve for z. In order to do that, I have to use the distributive property and distribute the 7 over each of the terms inside and distribute the negative 2 over each of the terms inside of its set of parentheses. The 5 just kind of hangs out. This gives us 7z plus 49 minus 2z plus 14. Notice the negative 2 times negative 7 changes the sign. Now we have like terms that are already on the left side of the equation right here. Don't make the mistake of adding 2z. They're on the left, that wouldn't be balanced. it would have to be on opposite sides of the equals. So we say 7z minus 2z is simply 5z. Then we combine the constants on the left, 49 plus 14, which gives us 63. Then we have the equal 5. We want to solve for z. So after simplifying, we're going to then subtract the 63. So we're going to isolate the z term. This gives us minus 63 on both sides, which leads to 5z equal to, well, negative 58. Then we'll divide both sides by 5 to isolate z. The last thing we need to do is check for extraneous solutions. There's always the possibility of a false solution when you multiply by the lowest common denominator and it has a variable in it. It's always a possibility. So checking is mandatory. We go back to the original to see what values we left out of the domain of this equation. We said x cannot be 7 and it cannot be negative 7. But we didn't get either value, and so our solution is negative 58 over 5. Let's work the next problem. Actually, come to think of it, problem 5 is a lot like the last one. Let's skip it and go on to the next one. Let's look at problem 6. It looks deceptively easy. Is it really easy? Let's find out. In problem number 6, we're given the rational equation b plus 4 divided by 4b. You cannot cancel the b's because of the plus 4. The only thing you can do is bury the b plus 4 in parentheses. It's not a b by itself factor. It's a b plus 4 group factor. Factors are things multiplied or divided by other things. You can't cancel a b by itself with a b plus 4. The second term is b divided by 24. And on the right side of the equation, we have 1 divided by b. When we're looking at the original denominators, notice that if 4b were equal to 0, b would have to be 0. So we know b cannot be 0. 24 is not a problem in the denominator. But again, from the third fraction, we know that b cannot be 0. This is our restriction on the possible solutions that we can get. B cannot be 0. Now we want to build our lowest common denominator. My denominators are 4b, 24, and b. To build the 4, I'm going to write 2 times 2 times b, leaving space for other numbers. For 24, I can think of it as 4 times 6, which would give me 2 2's again for the 4, times 6 would be, well, another 2 and a 3, but no b is necessary. For the last one, I just need 1 b, which I line up under the other b. Now I draw lines to indicate what the lowest common denominator of all of these little denominators is. I need 3 2's because 24 needs 3 2's. I need 1 3 because 24 also needs the 3. And I need 1 b because the first denominator needs a single b and the third denominator needs a single b. I don't need b squared. It wouldn't hurt. It would give me an equation I could solve, but it's overkill. 2 times 2 times 2 is 8, and 8 times 3 is 24. This gives me 24b to serve as my lowest common denominator. Now I'm going to take the original problem and multiply each fraction, each term, by the lowest common denominator divided by 1. Now I can cancel like factors, but they have to be factors. That means I'm going to have to take the b plus 4 group and put it in parentheses. Either the whole thing goes or none of it goes. It is not a b by itself because it's being added to 4. Factors are things multiplied only, not things added or subtracted. The rest of these are things that are only multiplied or divided, so they're already in the right form to reduce. I have 24 divided by 4, which will leave a 6 behind. I also have b, which divides by b, and that leaves no b constant behind. That leaves me 6 times the quantity b plus 4. Notice that I reversed the order by commuting it. In the second term, I have 24b in the numerator times b over 24. I reduce first by canceling the 24, and then I multiplied the b by b to get b squared. On the right side, I have 1 times 24b over b times 1. I reduce first by canceling the b's to get 24. After multiplying by the lowest common denominator, I want to simplify what I have, and I start by distributing the 6 over the b plus 4. That gives me 6b plus 24 plus b squared equal 24. The next thing I need to do is get my like terms together. I have a constant on the left and a constant on the right. I'm going to reorder so that b squared is at the front like it normally is, and then I'm going to move the constants together. The next thing I can do is subtract the 24 on the right to move it to the left. I'm combining my constants. Uh-oh. When I did that, they canceled, and I got left with b squared plus 6b equals 0. Relax, we haven't done anything wrong. It's correct so far. This is still a quadratic equation because of the squared term. I can solve by factoring, square root property, complete the square, or the quadratic formula. Factoring is always the first thing to check in case it factors. Often it does factor in homework problems. On this particular problem, notice that there's no constant term left, so it won't factor as the product of two binomials. The best thing we can do is take out a greatest common factor. I have one. I have a b in at least both terms, at least one. I'm going to take out the greatest common factor, which is b, by dividing it from each term. And that leaves behind the group factor b plus 6, and still equal to 0. Now I solve by using the zero product property. Remember, the zero product property is the one that tells you if two things, the b and the group factor b plus 6, are multiplied together and you get 0, one of these things has to be 0. And that means either b equals 0 or b plus 6 equals 0. Solving b plus 6 equals 0, I get instead that b equal -6. This is two possible solutions, 0 and -6. But wait, we're not done. Whenever we have a rational equation, we have to check for extraneous solutions. Scrolling back up to the top where the problem started, we note that, we said b cannot be 0. What that means is that our solution b equals 0 is actually extraneous. It does not work. If you were to try to plug it into the original, you'd have division by 0, which is just not allowed. So the only possible solution is the -6. The next problem is rather similar to the previous one, except note that it's already solved for 0. This is not a problem. Remember, we can turn -3 into a fraction by putting it over 1. You'll want to factor the x squared minus 16 first into x plus 4 and x minus 4. This factor here, x minus 4, cannot be factored any further, but because of the subtraction, it has to be put in parentheses. Then you build the lowest common denominator and multiply all 3 terms, well, 4, including the 0, by the lowest common denominator. 0 times anything is 0, so it stays 0 on the right. There will be some values that x cannot be, namely 4 and -4. You'll need to check for extraneous solutions, but I'll leave it to you to do this one at home. Let's see if there's another problem that we'd like to tackle here in this video. Problem 8 is not like one of the ones we've seen before. We have 2 variables present, c and r, but it's telling us it wants us to solve for r. This is a rational equation where we need to isolate r. Note that this also means that r cannot be 0 because it starts in the denominator. Let's solve this problem for r. The 2 pi is one term by itself, and the c divided by r is the other term by itself. In other words, I can turn this into 2 fractions, one on either side of the equation, by writing it as c divided by r equal to 2 pi divided by 1. Then I can use cross multiplication to get rid of the denominators. I could also use the lowest common multiple, which is just, of course, r. I could multiply both sides by r, which has the same effect as cross multiplication. Cross multiplication can only be used when you have one fraction on the left equal to one fraction on the right. When I apply it here, I get c times 1, which gives me c. When I apply it here, I get 2 pi times r. Then I solve this for r by first dividing both sides by 2 pi. That cancels the 2 pi while I'm isolating the r. This gives me r equal c over 2 pi. Or if you want to turn it around, you can write r equals c divided by 2 pi. Either one is correct. Notice that they already have r equal here, so we don't need to enter that part of it. We simply need to enter the c divided by 2 pi. But be careful. It will do the order of operations without exception. That means that if you enter the following, it will be wrong. Remember that multiplication can be entered with the asterisk, but it shouldn't be necessary when it's next to pi. You enter pi as pi. This is going to be wrong. It looks the same, you say. What's wrong with it? Let's look at the preview and see how it interprets this. It put the pi in the numerator because it followed the order of operations religiously. It took the c and divided by 2 and then multiplied the result by pi. We don't want it to do that. We want it to divide by both the 2 and the pi. So the 2 pi needs to be in parentheses. Now check the solution again. Bingo, that's correct. Let's see what the next problem looks like. This one is asking us to solve it for W. Again, we have a single fraction on the left and a single fraction on the right, so we can use cross multiplication. Then you want to isolate the W, treating the A like any other term. I'll leave it to you to solve this one at home. Look at this final one. We'll take a look at this one. This is 1 over P plus 2 over Q equal 4. When I have 1 over P, the denominator is P, and 2 over Q, the denominator is Q. And for the 4, I can write it as 4 over 1. This means, of course, that P cannot equal 0 and Q cannot equal 0. It's okay to have 1 in the denominator. Because I have 3 fractions, 1, 2, 3, I have 3 terms here separated by the plus out in the open and the equal sign. That means I cannot use cross multiplication. So instead, I'm going to find the LCD. P becomes, of course, just P, and Q is just Q. But P and Q are not the same. So I need 1P times 1Q. My LCD is PQ, or P times Q. Now I'm going to multiply by the lowest common denominator on each fraction, which is each term. In the first fraction, the P's cancel, and that leaves me with simply Q. In the second term, the Q's cancel, and that leaves me with 2 times P, or 2P. On the third side, I have 1 times 1 in the denominator, which is 1, so I don't have to write it, and 4 times PQ. That gives me 4PQ. Now, what am I trying to do again? I've already forgotten. Look back. It wants us to solve for P. To solve for P, I need to isolate the P terms first. To isolate the P terms, I'm going to move the 2P to the right by subtracting it from both sides. These are not like terms because this is a minus 2P, which is the P term, and this is a 4PQ, which is a PQ term. The best I can do is write them side by side. That leaves Q by itself on the left and 4PQ minus 2P on the right. I'm trying to isolate P, so the next thing I want to do is factor out the factor P. I don't need the greatest common factor because I'm only looking for the P. This gives me, on the right side, P times 4Q minus 2. Notice I didn't take out the 2, which was also a common factor. I just want P. This is still equal to Q. To isolate P, I need to divide both sides by the 4Q minus 2. This gives me P on the right and Q divided by 4Q minus 2 on the left. I know it's tempting, but you cannot cancel these Q's. This has subtraction next to it, and anything with addition or subtraction touching it cannot be reduced. This is simply the final result that we have for P, with the caveat that P, of course, cannot be 0. Let's enter this in and see what we get. This becomes Q divided by the quantity 4Q minus 2. Close the quantity. Oops, wrong one. Now we'll check our answers. Got the green check, gotta love it. That's the end of this particular homework set. And I hope that this did make sense to you and that you now understand how to handle rational equations. They're not easy, but never forget to check for extraneous solutions.